Hi and welcome to Maths class. Today we're looking at similar figures. Now we've already looked a little bit at similar figures and what they are, but particularly what we're looking at today are the tests for similarity. But let's just remember what similar figures are. Two figures which are similar will have the same shape, but they will have a different size. So all the angles that are corresponding will be equal and all the sides will be in the same ratio. And to remind you what that means, for example, in the triangle I'm showing you, maybe the second triangle has side lengths that are double the first one. So that would mean the side ratio is 2. So what you see there are our triangle tests for similarity, and they're very similar to the congruence tests, but with one key difference, and that is that wherever in congruence we're looking at side lengths being the same, for triangles we want the side lengths to be in the same ratio. So that means in order to test it, we need to test at least 2 pairs of sides. We find the ratio of one pair, and then we check if there's another pair that has the same ratio. Whereas with congruence, sometimes it was enough to check one pair of sides are equal, but equality is not what we're looking for. We're looking for a ratio, and we're looking for the ratio to be the same everywhere. So either we don't need to test it at all, and if we do, we need to test at least 2 pairs of sides. So our first one looks very similar to the congruence, side, side, side. But in this case, all pairs of corresponding sides have to be in the same ratio. And I'm going to show you how to use these shortly. The second one is side, angle, side, which means we need 2 pairs of corresponding sides in the same ratio. And then the included angles must be equal. Now remember what included angle means. If I've got 2 sides of a triangle right there, okay, my thumb and my finger, the included angle is this little join here. So if I made a third side here, then there's only one possible length that could be. Therefore, there's only one possible triangle I can make. So that's my side, angle, side. My angle, angle, angle is that all pairs of corresponding angles are equal. And I'll talk a bit more about that in the next slide. And then the RHS, right hypotenuse side, says we've got 2 right-angled triangles. We're going to compare the 2 hypotenuse and one other pair of sides, and they will both be in the same ratio. So what I'm going to do now is have a look at how these triangle tests look like compared to the triangle tests for similarity. Okay. Oh, and I need to move me. Hang on. Let's just get rid of me for now. Okay. So for congruence, I'm looking at side, side, side. All pairs of corresponding sides are equal. For similarity, it's the same, but in the same ratio. For side, angle, side, in congruence, I'm looking for 2 pairs of corresponding sides being equal, whereas for similarity, it's again in the same ratio. But in both of them, the included angle has to be equal. So these are very similar so far. Now, there is something different in the next one. ASA is angle, side, angle, because for 2 pairs of triangles to be congruent, they need to be the same shape and the same size. So the corresponding angles tells me about shape and the corresponding sides tells me about equal. And remember, I only need to test 2 pairs of angles because then I know that if 2 pairs of corresponding angles are equal, then the third will also be equal because they must add up to 180 degrees. Now in similarity, we don't need to test the side lengths because as long as I know that all the angles are equal, then I know that the shapes are the same, and it will be true that the sides will be in the same ratio. I know it's true, but I don't need to test for it. Now it says AAA, but in fact, as long as I know that 2 sides are equal, then I also know that the third side will be equal. And the last one is also very similar. RHS, I've got a right angled triangle. I'm testing the hypotenuse and one other pair of sides, but in congruence, I'm testing that they're equal. And in similarity, I'm just testing for the same ratio. All right. Now we're going to go through a worked example that shows how to do a proof that 2 triangles are similar. And it's really important that you take notice of this example, even if you think you know how to think through why two triangles are similar. An important skill is being able to write all the working that's required in a proof, okay? And if we put one of these on a test and you don't know what you need to write down, then you're not going to get all the marks, even if you think you know how to show this. So please do watch this example. All right, so I'm asked to prove that in this diagram, triangle ABC is similar to triangle DEC. Now notice the notation here. That means triangle, that means similar, and that means triangle. And by saying triangle and then referring to 3 points in a row, I mean the triangle that is made when I join these 3 points, A and B and C, and then back to where I started. Okay, and that means similar. So first I'm just going to think about how would I know that these are similar. We've done a very similar one to this in Congruence. And so the first thing I'm going to look at is the fact that what am I given? Well, I'm given a set of parallel lines here. And if you remember, we revised parallel lines in another video, which you should have watched, and we learned about this thing called alternate angles, which are equal. If you don't know what I'm talking about, please go back and watch that video. I'm not going to explain it again here. So, I have parallel lines, and if I extended these lines a little further, right, just like that, if I imagine those lines, they're parallel lines that keep on going. So then this line here is effectively a transversal that goes across. It's the equivalent of this line going through those parallel lines. So if I look for a Z shape here, if I turn it around, that might make it a little bit clearer. I look for my Z shape for my alternate angles. I can go along here and then down here and then down here, which means that I can put a point in the place where the two angles are equal because they're alternate. So the first thing I'm going to write down is that this angle is equal to this angle, and I know that because they're alternate. So angle BAC. Notice the way I refer to the angle. It goes from B to A and then to C, is equal to, and now I'm going to go from E to D to C, angle EDC, and the way that I know that is alternate. They are alternate angles, which means they must be equal. So what I've done in my working is I've identified two angles that are similar, and I've given a reason that I know they're similar. Now I can easily see another pair of triangles, sorry, not similar, a reason I know they're the same, two angles that are the same. Now here's another pair of angles that are equal, these ones here. That's because they're vertically opposite angles. So I'm going to write that down. ACB, angle ACB equals angle DCE. For the same reason, vertically, or not for the same reason, but I'm giving a reason, vertically opposite. So I've identified two pairs of angles that are equal, and I've told you how I know they're equal because they're vertically opposite. Now, I could say that these are another pair of alternate angles, but the other thing I can use is I know that angle I've done BAC, angle ABC will be equal to angle CED, and I know this because the other two pairs of angles are equal. So angles in a triangle sum to 180. See how I'm using shorthand so I don't have to write stuff out? But it should be clear. This symbol means angle. So angles in a triangle sum to 180. That's how I know that that equals that. But I could just as easily have written alternate angles because they make another Z shape here. All right. Therefore, I have shown angle, angle, angle. That is the shorthand for one of my 4 tests for similarity. Therefore, triangle ABC is similar to triangle DEC. Don't skip that last line. You'll lose your last mark if you do. All right. I'm going to show you another example. So here's my second worked example. I have to prove that the first triangle, triangle ABC, is similar to the second triangle, triangle DEF. Now I'm going to look at the information that I'm given. This looks quite different. I don't know everything about the angles. I definitely can't go for all the angles being the same, but I do have quite a few sides given. So I'm going to match up the sides. Now, assuming that these two angles are corresponding because they are equal, that means that AB and DE will be corresponding. That also means that AC is a corresponding side to DF. So I'm just going to go back to my triangle tests for similarity. If I look at the second one, side, angle, side, two pairs of corresponding sides are in the same ratio and the included angles are equal. And that's definitely what I've got in my diagram. If I have another look, I can see that these are two pairs of corresponding sides. I have to check if they're in the same ratio, and these are the included angles because it touches both sides, right? So let's have a look. First of all, I'm going to write down the most obvious thing, because even if I can't figure anything else out, you never know, there might be a mark in it. I can see that angle BAC is equal to angle EDF. And wherever I can, I try to put them in the same order. So BAC and EDF, I didn't write FDE, just put it in the same order. It sort of really highlights the fact that these are corresponding. And how do I know that? It's shown. It's given to me. I could have written given, something like that. Okay, now I'm going to test the ratios. So DE divided by AB equals 9/3, which equals 3. So far so good. Haven't shown anything yet. FD over CA equals 13.5 over 4.5, which also happens to equal 3. Okay, so what I've shown now is therefore two pairs of corresponding sides are in the same ratio. I'm also going to point out that 50 degrees is the included angle, meaning it's the angle that touches both of those sides. That's important for SAS, right? Therefore, SAS, that's my shorthand. Therefore, triangle ABC is similar to triangle DEF. And that's my last worked example.